Hello and welcome to Physics Problems One by One.
So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself.
Starting new playlist, momentum. So momentum is mass and V, and we multiply one over another. This is momentum. This is momentum of the body, point mass, m, that travels with speed v, and this is m multiplied by v, and of course this is vector. This is vector because velocity is vector, speed is vector, then m multiplied by v is vector. And it's not much complicated in the beginning, because the second law of motion is ma equal f. And if we say, let's consider very small time, change in velocity equals f. And that's all. But if we put m inside, because what is change? Change is mv final minus v initial, t final minus t initial, and this time is very, very small, equals f. And they're already writing it in the projection, let's forget about vectors. And if we multiply this, m on this, we have mv final minus mv initial, and this would be delta t equal f, and mv final would be momentum. Let's put it p, momentum, p final minus p initial divided over delta t equal f, and p final minus p initial is delta p. Delta p divided over delta t is f. So essentially this and this, of course we should put vectors, it would be absolutely the same. But for all our goals and purposes, this would be second law of motion, but in a slightly different form. And then they do a little bit of a change. They say, oh, okay, let's imagine that we have a collision. It's all good for collisions. Let's say one body collides with another, and the force, if the force is constant, and this is time, this is force, and this is delta t, and this force doesn't change. Suppose one body hits another body and there is force between them and it doesn't change, then this law would be delta p over delta t equal f. And then would be delta p equal f multiplied by delta t, and this would be this. This would be surface under the graph of t. This is integral, this is calculus, that's what I was talking with you when I was talking about kinematics. But delta p equal f delta t if f is constant. But let's consider a situation when f is not constant. When f is not constant, then we still can divide it on very small intervals. Each interval would be delta t. On each interval we can consider that this f doesn't change, and this would be f1 delta t, and this would be f3 delta t, and on each of those it would be delta p, change of impulse. So total change of impulse would be the whole area under this graph. But for us it's not that really important. Let's consider the case when the body falls. This is h height, and it goes down and it hits the bottom, and let's consider that this is delta time t is very, very small, let's say 0.003 seconds. And during this time it bounces back. Let's consider that it's absolutely elastic. So this is V, and when it bounces back it would be the same V. But all of this happens during the 0.03 seconds. So how can we act? We can say basically, and they want to find us the average force. So F average that acts on us. Obviously this average is N, normal reaction of the surface. So when body goes from here, going with V0 down, and we immediately can calculate V in this case, because remember H equal V squared final minus V squared initial, which is 0, over 2G, H equal V squared over 2G, and we immediately can say that V equals square root of 2GH. Square root of 2GH. This is the speed with which we're approaching. Alright. So now we can say who acts on us? Who acts on this body? This body during this period of time is subject of two forces. mg is still there, and then N. And of course N is bigger than mg because it creates acceleration up. Because speed, initial speed is this, final speed is this, we can have delta V. Delta V, and of course we have to act in this axis, is V final minus V initial. And V final is V 2GH minus, and initial is another minus because it's directed down and it's exactly the same, 2GH. And so it would be 2GH. This is the change in speed. Accordingly, the change in the impulse would be m delta v, and it would be 2m 2gh. We know delta p and we know delta t. So, of course we can say that delta p divided over delta t, those two values are known to us, equals the force, sum of the forces that acting on this body, and it would be n average. This is average because of course when we only hitting it slightly the force is very small, but when we press the force is very high, so this is average. Let's put average minus mg, and of course if we move it otherwise around, we will see n average. We isolate it, mg goes here, equal mg plus delta p over delta t. And so delta p over t is this, so we know n average equals mg plus 2m 2gh. And this is the formula that they want us to receive here. So once again, what's going on? The body goes down, hit the surface, comes back because it's elasticity, full ideal elasticity. It goes here, and the speed is exactly the same, and we can find delta V. It's V final minus V initial. V final is this, V initial is this. V final, we know that it is 2GH because we analyze this, it's just kinematics. And so minus minus because minus, but V initial is directed down, so it should be taken with minus, and thus would be 2GH minus double. So we know delta P, mass multiplied by this, and this is known value. Mass is given, H is given. And then we have to plug delta P over delta T. Delta T is given, delta P is this, we know. And average it would be this, and I of course forgot delta P divided over delta T. Here, delta P I put correctly, but I forgot to divide on delta T. Alright. And next installation would be partial elasticity and totally non-complete inelasticity. Like, subscribe, bell, question, comment, your problem. See you next time.